Good morning, everyone. Can you hear me? Can someone tell me if you can hear the sound? Good. All right. Thank you. So we had lecture 14 today. There are a couple of announcements, and then I'll start with the lecture. So final exam. Let me see. Where is the final exam? I believe it is December 17th. Let's see, 1 second. Yeah, December 17th, 12 to 3. So that's a final exam. Don't forget that. I'm sure it is in your calendars. But December 17, 12 to 3. Okay. Everything will be covered in the final exam. Mostly no programming. Mostly homework type of questions. So today we are doing lecture 14. There are in total 17 lectures. So I will do lecture 15 tomorrow. And then the following next week, we will finish lectures 16 and 17. After that, I have time. So what I'm going to do, I'm going to review. So it will be a couple of lectures of review. If you want me to do review anything, we have to do that. And also, I plan to do the homeworks in class. Yeah. So that would be a good practice for everyone. Project, the details of the project will be announced on Monday. So you will have 2, maybe 3 weeks to finish the project. Project is not very hard, very similar to the lab, maybe a little extra difficulty. Other than that, there's not much into the project. So we will expect the details there. But important thing about project is it is 20%. So you have to do a good job, better job than lab, because lab there are 6 or 7 lab. It is average, but there's only one project for that 20 marks. So you need to do a good job with the project. And then I have an announcement about plagiarism. I came across in the submitted lab reports, there was some instances clearly copying. We could see that first of all, the Replit allows to see the history. So you are supposed to work in that so that you can see your work. If the code just appears, that is suspicious. The fully completed code appears, that is suspicious. And we will just see, and it's easy to spot that. You were given enough guidance to work on your own on this. The help is there, so there's really no reason to do that. And you are just not doing yourself a favor by copying. You pay all this money and then copy. It doesn't make sense. So, but it is a serious offense. So that's I wanted to remind you that this is very serious copying. So okay, it is not just that. If the code just appeared, I know you can work on some other external IDs. That's fine. I'm not claiming that, but I'm only asking you to work on your own. but we are not. History is one good thing, but even if the code just appeared and we found in standard, it's not about even you, Sydney. We have other ways like similarity in code, examples, things like that. That is what we are. Not history. Having a history in Replit is not a requirement. So yeah. Yes, if you just work on your own, it is hard. There is nothing. We will. I don't think we. A couple of instances we found that not really about history. It's about similarities. So anyway, so that I just want to emphasize this. Very important. Worst outcome is I have to report this when I find it to the high level, and then they will take action, and also the worst case outcome is not even transcript. It might be termination from the university. That's the worst outcome. I wanted to remind that. So that's very important. Okay, so that's out of the way. This is a very small lecture actually, and pretty easy lecture. So numerical integration. So we all know what is integration. So if we have a function, integration means integration. So what is integration? Integration is the area under a curve. So if we have a function fx, and let's say this is b, a integration of fx dx from b to a, we call it I. So that is area. So that area is the integration. Yeah, and a certain interval can be computed using integration. This course, there are integration itself. It's a different concept, but when it comes to a function, and then this one under this interval integration means area. So that is the type of integration we are going to focus in this course. So how to find area of a function between certain intervals. And of course, this is not, if you have a function, let's consider a function fx is equal to alpha x squared plus beta x plus gamma. If you want to find the integration of this function between a and b, you just integrate between a and b dx. And the analytical integration of alpha times x cubed or 3 plus beta times x squared or 2 plus gamma x. And you just give the limits b a. So substitute x is equal to b and compute that whole thing. Substitute b x is equal to a and compute and subtract them. So that's how we find. So alpha b cubed over 3 plus beta b squared over 2 plus gamma b minus alpha a squared over 3 plus beta a squared over 2 plus gamma a. That is the integration. That's the analytical way of computing integration. So that is the analytical solution. This course is about numerical approaches. So if you don't know a function, for example, if you have a function fx is equal to b to a e to the power x squared, something like a pretty complex function, or some function, that is not even defined. You just have some data point. We don't even know. We don't even have a function. All we have is a bunch of data point that we measured at some interval, and we need to compute the integration. So the red curve is absent. What we have, some data points, and how to compute. What is the area? What is this area? What is this area? So there is no function. So that is a classical problem, numerical integration. So that's, we're going to study three different approaches: trapezoidal rule, Simpson's one-third rule, and Simpson's 3/8 rule. So let's jump into trapezoidal rule first. Before I go into trapezoidal rule, how are we going to do this? So this figure one gives an example. So if the blue curve is the function, so that's the function, and then let's say we want to find the integration between a and b. We don't know the function. We don't know the function. We only have these values. Values. Midterm grade should be posted. I mean, probably today. Yeah, it is already last week here, but I know that it was already graded sometime today or tomorrow. It won't, not later than that. Okay. Thanks for reminding. I last week here what's going on. So let's say we have these points. So if you have also, if you can make a rectangle around that point, and then you can find the area of this stripe. Since it is a rectangle, the area of rectangle, if it is A and if it is B, area is A times B. That's the area. So we can compute that area, and then we can compute this area. Then using rectangular approximation. So this is called strip approximation, or we can approximate make strips both ways, and we can make grids. So area of each of these grid, all of these grids are the same. So you just find how many grids, and then the the area. So but then it is an approximation. So we just look at these edges. Some places it is fine. So that is the edge. That is the area we want to. That is the range we want to find the integration. So if you just look at the edges here, for example, if I just take this area and there's a gap there, and it is overflowing, it is not filling. That is called the add up as error. So there's always, when you do numerical integration, there will be errors. And it also depends on if it is a true function versus if it is just the data. Sometimes we won't even know how much is the error. But what we know is that there will be some errors. That's always the case for all the computation that we have been doing so far. There will be errors when you use computer to solve problems. Problems like this, like practical problems. Okay, so let's take one of these stripes, and that is what is shown here. Let's say there's only one stripe like this, and then it is A and it is B. So the area of this, if that is a curve, and if we are just approximating that curve using a trapezoid, well, when I said rectangular approximation, actually, if you just zoom in, that can be, rather than doing a rectangular approximation, if it is here, when we say stripe, indeed that was a rectangular approximation. But here we are doing it a trapezoidal approximation, because that's going to be a little bit better than rectangular. But if it was a rectangular approximation, I was going to do this. and then I was going to compute the area of that. Compared to that, trapezoidal approximation is integration is a bit more accurate. There are theoretical proofs for this, which we won't get into, but I can tell you that, and it is some formulas about this. The error analysis is in the book. This book you can take a look, but it is well known that rectangular approximation and then trapezoidal approximation, that is actually what we are studying. We are not even studying about the rectangular approximation because it is so simple. And then Simpson 1/3 and Simpson 3/3, the accuracy of this increases. So the accuracy increases. So Simpson 1/3 rule is better than trapezoidal rule. Simpson 3/3 is better than Simpson 1/3, and obviously trapezoidal is better than rectangular or strip approximation. So if we have a limit a and b, and if we know the data at these 2 points, then this one gives b minus a, that is this height, times the summation of these 2 heights divided by 2. That's the formula of an area for a trapezoid. So that's how we will compute that. And then we can also use Taylor series approximation to do the same. So what is done here is we just approximate the function using Taylor series, which is, if you remember, Taylor series fx is fx0 plus h times f prime x0 over 2 factorial plus h squared times f2 x0 over 3 factorial and so on, right? Is that right? So use a one-term approximation. So sorry. Let me get this right. I missed a mistake here. Okay, so the approximation, the first order approximation of the function Taylor series approximation fx f x0 plus h times f prime x0. So there's no 2 factor, that's for the next term. So if we approximate the function, so sometime, it has been written many, if we can write x0. If h is the difference between x0 and x, it will be x minus x0 prime x0. So f prime, if you look at this, f prime in fb minus fa, so that is fb minus fa divided by b minus a. So that is f prime x0, and then x minus a. So that means a functions here as x0. Our traditional Taylor series expansion. This is x0. So we are expanding the function around a. So we are expanding the function around, writing it x0. It's a comfortable read because when you study Taylor series, we call it x0. So this Taylor series expansion expands the function around x0. So that's why. But here Here we are expanding it. In this example, we are expanding it around FA. So take the first order approximation of the function. Now we know how to integrate that. So when you integrate that, so it is a function of x. FA and FB are not those are constant values. So if you just integrate, you will see it comes to this very well known formula. We already know what is the area of what. This thing is not right. Okay, so that trapezoidal equation integration formula that I'm sure you all know, it can be proved. So using Taylor series, there's nothing much there. Probably when we studied this formula for trapezoid, we used geometry to prove. Probably that was done in grade school anyway. But here there's a second proof for trapezoid formula using Taylor series. That's all. But it allows us to expand this for multiple stripes. So let me give a picture here. So if we have a function, so if we have a function and we have, let's say, multiple stripes. These are all equal length, so it is not coming that way. Definitely, this is all h. So we just divide the x-axis into multiple stripes, and then since it is trapezoid, I'm going to connect them using a straight line. You see, that's a pretty accurate. Get the idea. So we are just connecting all of those. So that's, we are different trapezoids. So we had to just compute the area of each trapezoid and add them. So that is this formula. If you have multiple strips, you compute the area of each trapezoid and add them. So then we have a formula for that. So that is b minus a. This is b. This is b and this is a. The extreme 2 points, b minus a, divided by 2n. So n means there are n plus 1 points. So this, we call this x0, x1, x2, all the way up to xn. So there are how many stripes or how many trapezoids? There are n trapezoids, which means n plus 1 x values. That is x0, x1, f, xn. Sorry, no, there's no f. x0, x1, all the way up to xn. So n plus 1 x values and obviously n plus 1 y values. So if we have all of that, then the formula is first value fx0, last value fxn, and 2 times all the middle values. 2 times fx1, fx2, fx3, all the way to fxn minus 1 divided by 2n. So that's the formula. If you have n stripes, the proof is just on top. It's not very hard. You just sum all of them and simplify it as it is shown in equation 8. And it also makes sense that to increase accuracy, if we can get as many points, as the b minus a becomes smaller, that means you get more points. If you increase the interval, it will improve the accuracy. But in practical situation, you might not have the data. If you have the data, definitely you solve the data. That will improve the accuracy, at least according to this. Okay, so we are given an example here. evaluate the integral of 0 to 4 integration of x times e to the power 2x dx. This is an example just to check this algorithm. So the actual integration analytic solution is known, so we know what is the perfect answer. So the analytical solution is given. We are going to pretend that we don't know that, and we are going to make small trapezoids and see how close we get. We already know that as we increase the number of intervals, we are going to get the approximation. So the correct integration using analytical method is this 5216.93, whereas the first example we are just assuming 2 interval. So since it is between x0 is 0, the final x is 4. If it is 2 interval, x1 is 2 and x2 is 4. So there are n is equal to, so in this case n is equal to 2 in this notation. Okay, so here I'm using x0 x1, the last value is n, so here n is equal to 2. So just substitute the values for formula 8 and we will get, and this is the value we get for the integration, that is 121, 42, 22, and you can see that they are not even close. Just because it's a very nasty function, I don't even know how does it look. It is e to the power 2x times x, so probably something like this is happening. So e to the power x is e to the power 2x, something like this, and then on top of that we have x. So it is definitely a nonlinear function, something like that. So if you approximate using a trapezoid, you can see we will make errors. So since it is e to the power 2x, that is going to be pretty steep. That is going to be more steep than, and draw this and check, but it's going to be something like that. So that's why the error is pretty high. I'm wondering if these numbers are correct. That's too big. Can someone check this? So that's what? Not correct. So maybe that's, let me check this. That doesn't look right. Let's see. 1 second. Can someone see if equation 12 and let me know? Just punch those numbers. E to the power 8. We have e to the power 8. Right. Okay, let's open the book here. No, I'm talking about this. If you can see the screen, can you compute this value? There's some mistakes here in my equation. Analytical solution is at least okay. So the analytical solution. So you're saying that this. I need to check this. This doesn't seem correct, but you're saying this is correct. E to the power 8. Okay, let me do it here. Okay, so how about this? I will ask you to check this, and I will also check this and update my lecture notes. But this last part doesn't seem to me. Okay, I see what's going on here. Okay, sorry. So what is the problem here is this. So first we substitute n is x is equal to 4, and then we substitute x is equal to 0. So instead of that is a negative. That was the problem. Okay, when you subtract, the answer is that. So yes, there was a negative sign missing. I'll fix it later. So you get the idea. So when then you increase the number of interval, you can see we got if here we change to n is equal to 4. So here n is equal to 4. So we have now 1, 2, 4 intervals instead of 2 intervals. Now you have 4 intervals of 4 trapezoids. And when you increase the number of trapezoids, you get a value. You can see that is getting closer. It's getting closer to the true value. So that's trapezoid method. You divide the area into small trapezoids and then use that formula. So that's a formula for trapezoid equation 8. It's the trapezoid n interval formula. As I mentioned earlier, there's nothing tricky about this lecture. Probably it's one of the straightforward ones. Okay, so yeah, there is no, if you have to write an algorithm, you can just think about how to write, basically you have to write an algorithm to implement equation 8. That's also very straightforward compared to all the difficult ones we had, like Gaussian elimination. Okay, now we are moving into Simpson's 1/3 rule. Again, it is, let me give a, see how this the approach works. So it would be nice to compare it with the trapezoid method. So when you had a function, we said is a function, we just took some points on the function and approximated them. So we just connected them using a straight line. So that formed the trapezoid. That formed the trapezoid. Whereas in Simpson, we will take, especially for Simpson's 1/3 rule, we will take 3 points, x0, x1, and x2, and then we will fit polynomial around these two, because if you have 3 points, 3 data points, so x0 and then fx0, and then fx1 here and fx2, so you have 3 points, you can fit a second order polynomial through this. If you have only 2 points, if you only had 2 points, you can only fit a straight line, because you had the straight line will be y is equal to x plus c. You can compute m and x using these 2 data points. So if you have 3 points, you can fit a polynomial so that particularly y is equal to a0 plus a1x plus a2x squared. Second order polynomial. We can fit a second order polynomial. On that note, when we add there, if we have 4 points, that is actually Simpson's 1/8 rule. We can fit another polynomial, higher third order polynomial. That would be written as y is equal to a0 plus a1x plus a2x squared plus a3x cubed. So we need to compute these coefficients a0, a1, a2, a0, a1, a2, a3, and here, if I write in the same fashion, I will write it in is equal to a0 plus a1x. So here also we needed to compute a0 and a1. So basically this is when you compute the polynomial and integrate it, that became the trapezoidal rule. When you approximated, took 3 points and approximated it as, it became a Simpson rule. Simpson's 1/3 rule. You take 3 points and approximate, it becomes Simpson 3-8 rule, it is called. So you can see that natural, these are all related. They call different names, but these are all related, that we are approximating the function as a polynomial. Here we approximate as a first order polynomial. Here we approximate as a second order polynomial, and here we approximate the function as a third order polynomial. So all these three methods that we are studying in the lecture are related that way. And then why it is called Simpson's method? Well, Simpson invented an approach, an easy approach to compute that integration. So what steps involved in computing that approximation? First, you need to find A0, A1, and A2, and then you have to integrate. So you find A0, A1, and so steps: find A0, A1, and A2, and then find A to B. Instead of X, I'm going to say Y, Yx, Dx, because as you know, this Y is a function of Yx. So find Y. So all of this is done in a very nice form by Simpson. So first they used the Lagrange approximation. If you write the function, instead of writing A0 plus A1x plus A2x squared and trying to find A0, A1, and A2 using 3 data points, that involves solving a 3 by 3 system of equation. If you write the function, this is a Lagrange already found out. You can write that function like this. So the second order function, this we already visited this in the previous interpolation lecture. So this is in that form. This is Yx, indeed is in this form, A0 plus A1x plus A2x squared form, except there's no A0, A1, A1, A2. Everything is already computed. Instead of A0, A2, everything is computed here. So that's the beauty of this. So we didn't do any extra computation. So the next step is to elect into these 2 points, or x0 and x2. That is done by Simpson, and then they came up with the answer that this will be the integration. B minus a O times fx0 plus 4 times fx1 plus fx2 plus fx2 divided by 6. So if you compare this formula, and if you apply the total, you will see that there's a small difference. So if you have these, you can also use this trapezoidal approximation to find this. You will see that first of all the formula is different, but it is already proven that this is more accurate. That's not going into the proofs and everything, but just assume that's Simpson's 1/3 rule. But we will verify it using the same example. Okay, so that is a formula, b minus a. So this kind of, I mean, I don't ask the student to remember formulas. Obviously, if it is a typical final exam, I would have given the formula at the back of the exam sheet. Since this time it is take home, you don't need to worry about it. But the important thing, you need to understand concepts. So that's the formula. If you have 3 points, similar to before, what if we have multiple points? So let's say you have a function, like similar function, and then we have multiple points. And then if we have multiple points, we have many points, how do we apply Simpson rule? And that is the formula here. So that is b minus a. Let me make it a bit bigger. So that is so there are 2 formulas here. The first one, I'm going to put a box around it. So that is the Simpson 1/3 rule. with one instance. So you need 3 data points for the x0, x1, and x2, fx0, fx1, and fx2. So that's the first case. If you have multiple points and between the limits a and b, and if you have n points similar to here, x0, x1, x2, all the way up to xm, and then you can write the formula fx0 times 4 times I is equal to 1, 3, 5, so odd numbers values, fxi, and then the even numbered values fxi times fxn. And then it's important, this will only work, so the trapezoidal work method, multiples interval will work for any n, but here we have one condition that we have to use the formula, the n must be even. So we need to make sure that there are even number of formulas. That only when Simpson rule will work. So let's take the same example, and then we are going to compute it using one instance of Simpson's approximation. So that's we're going to compute between 0 and 4. So x0, x1, x2. So the x0 is 0, x1 is 2 is 4. So if you compute that, and we did that, remember in the previous example we did that. So that will be equal to our first case here in the trapezoidal method. So you just apply the formula, and then the value that we got for integration is 8,240. So let's go back and see what we got here. We got 12,000, whereas the true value is 5,000. Obviously, Simpson method using the same number of data points, the Simpson method gave the answer. So that's one of the takeaways from this, which I already mentioned, that using the same number of data points, Simpson one-third method gave a better approximation for integration compared to the trapezoidal method. So that's it for Simpson's one-third method. We are going into Simpson's 3/8 rule. So as I said, here we are approximating as a third order polynomial. So if it is a third order polynomial, we can write the third order polynomial using Lagrange method like this. There's no need to estimate the formulas because it's already given. If you use the Lagrange approach to write the formula, the coefficients are already known. So that saves computation, first of all, and find the formula. And then the Simpson came up with this, this formula that when you integrate it between x0 and x3, this time we need 4 points, x0, x1, x2, and x3. Is shown here, x0, x1, x2, and x3. So the formula for one case is, if we have for one instance, the integration will be this. There is b minus a over 8, fx0 plus 3 times fx1 plus 3 times fx2 plus fx3. And for multiple data points, we have 3 times b minus a over 810 times fx0 plus 3 times 1, 2, 4, 5 in that order, fxi, and then 3, 6, 9. So if you see what is going on here, in this summation, all the multiples of 3 here, sorry, so in the summation I am highlighting using green all the multiples of 3, and here everything else. 1, 2, 3, 3 goes to the next summation, 4, 5, then 6 to the next summation, 7, 8, 9 to the next summation, like that. And then you have the final one here. So yeah, if you had to program it, okay, that's a few if statements, but you can definitely easily program this approach as well. So why this is called 3/8 rule? Because of these coefficients, 3 here and 8 here. So that's why it is called 3/8 rule. So the first one shown in equation 25 is the single application of 3/8 rule, whereas the one equation 26 is the multiple approximation. So if we So n must be a multiple of 3. So so we are using the same example here. So we are using the same. Okay, one of the conditions. So ports, you can see these two. Mark 1. For Simpson 1/3, n must be even. Simpson 3/8, n must be a multiple of 3. That's one condition. Since n is a multiple of 3, also the difference should be, I mean, it is already assumed that difference should be h. The x interval should be the same. Now that is one of the assumptions, one underlying assumption. So that is probably one of the limitations of Simpson method. You know, if you had no control of the data points, and you got data for x is equal to 1, then 5, and then 10, and then 20, and then 22, and 23. No, uneven data points, we cannot apply Simpson method. So that is probably one of the drawbacks of this approach. So the x should be evenly spaced. So if we have to apply this, the same example we had, integration of x times e to the power 2x dx, giving us 0 and 4. So we have to find those points carefully. 0, 4. How many points? This is x0 and this is x3. So x1 and x2 needs to be equally spaced. So that will be 4 by 3, and then there will be 8 by 3, and then this is 12 by 3, which is 4, right? So this point x1 should be 4 by 3, and then x2 should be 8 by 3. So you have to select those 2 points, and then so if we have 3 steps, I don't know if we don't have a equivalent example in Simpson 1 that we might have one in Trapezoid. 1, 2, we don't have a 3-step example, we have a 4-step example here. But the value that we got using Simpson method for the same example, Simpson 3 is 6,800. So what we got as true value is 5,000. So we got closer than using 4-step from Trapezoid. It is already theoretical proven that higher order Simpson method is accurate. So if we can, the data supports us, we should use that. So that's all for integration, really. It's not much. This lecture, I don't want to start the new lecture today because it's better to differentiation. Different. The next lecture is differentiation. So that's I will leave it for the next class. So we have some time today, and do you have any questions so far on this, or any other questions really? If you have any question, we can discuss. Otherwise, we will just meet. I will have lectures recorded for Thursday. So we have some extra time today because this is a quite short lecture. It's 70. Okay, let's see. Yes, did I have an appointment with you? Did I send you an invitation, Sydney? I have a couple of meetings tomorrow, but I can definitely book you time. Give me 1 second. My Teams is not working. How about, okay, probably I did not. I was thinking about that, but how about later? Do you have time at 4? Okay, let me send an invitation for 4. I'm going to send an invitation through Teams so that you can accept it, so that we are booked. me a minute, and my computer is a little bit slow. I will announce. I will let you know. Definitely not this Thursday. Or there might be this Thursday. It's not bad. Yeah, I might announce that soon. Yeah, I will announce that. Not a bad idea to have a this Thursday. Hang on, my computer is taking some time. Okay, let's see. Okay, I'm going to book a time at 4:30. Sydney. I send you a request. You should receive a request and please accept it so that we are confirmed. Right, everyone. Have a good day. And so the next lecture, the lecture 15, numerical differentiation, will be posted, recorded, and posted. And we will meet live on Tuesday. There might be a quiz on Thursday. I will announce that in advance. I'll also let you know which lecture will cover. Bye now.